the interleaved memory, it's creating parallelism. And these kind of memories are actually good for vector facilities. They were utilized in vector facilities because essentially what you do is you start with an address, and then each block, each bank will give you an element of the vector. Then let's say if you have a vector machine where you have 8 items per vector and you have 8 blocks, you can get those vector items in a pipelined way out of an interleaved memory. Then you start again, you issue an address, which is the address of the vector. After some latency, the first element of the vector will appear. You start the calculation on it, and from now on, one cycle later will come the next one, and the next one, and the next one. And there is some beauty in the way you do the game with the bits of the address. And maybe it's good to look a bit on that. Okay, let us assume that this is 1 kilobyte memory. And this is 1 kilobyte memory, 1 kilobyte memory, 1 kilobyte memory. Those are memory blocks. Now, in here, I need 10 bits of address, which will do the selection of an item in here, or in here, or in here. But I need something more, because what I'm building now, what? You look very unhappy. No? You are only serious. No, you should not be serious. This is a fun course. We are just having fun here. I'm just building a 4 kilobyte memory. And then, in order to build a 4 kilobyte memory, I need more bits. Then I need other 2 bits in here, 2 bits, which will make the selection between those blocks. Then here I have a 2 to 4 decoder, and that will provide now signals for those. Those are called chip select. Okay? Then for a certain address of 12 bits, only one of those chips will be active, will get this signal, which is the chip select. Then based on this 10-bit memory, will provide the solution out. And in here, I have a 3-bus structure, and in here, I have 8-bit output. This is the way I'm making a memory out of 1 kilobyte blocks. Now, I can arrange those also in a different way. And I can activate all of them in the same time. Then I put them like that. And they all get the 10 bits. Right? And now they are all giving output 8-bit. And I use now a 4-to-1 max to select which of those I'm using. Are those schemes doing the same? Functionally speaking. Come on, it's not early any longer. It's late by now. It's almost noon. Then they are doing the same. In this one, I'm doing first the selection of the chip where I'm getting the item for, 1 out of 4, and then the selection of the location based on those 10. This one, it's activating all of them and is doing the selection at the end. Which one is better? The second one. Why?
First one.
The middle one then. The second one will burn more power because I'm activating all the chips. Then if I'm using it this way, then I'm just issuing an address and then reading the output. This one is better. Your neighbor is you are very busy with the computer. I don't think you have that on the computer now. No, you don't have to look here, right? You have a homework for some other course? Then I'm disturbing you. You know, goes on, you might write in the homework things which are from here, and then if I'm doing that, this is bad. This is good. Those are sleeping. This is active. However, if I want to access 4 consecutive locations, this will be a very good one. Because I'm activating all of them, and then after the latency, the access time, this will be ready. I'll put it out, and then it will take me the delay of the max until it's available. I report it for output, then I change the bit. I'll take this, and this, and this. And then in this way, I have 4 banks of memory, which I'm accessing in parallel, and I am giving output on a faster way. It's like a burst if you want. But I need 4 transactions on the bus in here. But after I initiate the transactions, they will happen very fast because the information is already available here. While if I go for 4 transactions in here, the overhead of bringing the information to this point will be larger. Now, there are some extra issues here. If I use, let's say, this is my address, okay? Now, here I have 10 bits, and here I use 2 bits. If I take those 10 to select things here, and those 2 to select things here, I will report bits 0, 1, 2, 3, starting from a set address of this one. But I don't have to do it like that. I can also do it in different way. And I can get what is called stride addressing. Then if I move those and I say no, I will take those bits. Then those 2. Okay? Now, this plus this 8 are used here in the selection. And those 2 bits will now give me values with a stride of 3. Then I'll get 4, 0, 4, 8, 12. Then by playing with the selection in here, I can get bits which are not consecutive in the address space in the same transaction. Do you get the point? Now, if I play with matrices, this may make sense. Because when I'm processing a matrix, depending how the matrix is stored, row-wise or column-wise, and depending how I'm processing the matrix, my values might be consecutive on the memory, or may be on a stride-based address. And I can play with this in order to get the kind of stride-based access. And I can even play that doing dynamic kind of reconfiguration. Then I have a memory system with a number of banks, and I can change at runtime how I'm doing the address scrambling. And then if I want, I can do, consecutive addressing. If I want, I can do with a stride of 4 or 8 or whatever. I can play only with powers of 2. Now, the way I'm dealing with this mapping will also have an influence on having addresses which I'm looking for in the same or in different banks. Let's say I want to do a stride address, and I'm looking on elements 0, 4, 8, 12, and I'm using those 2 bits. All those elements forget it about the advantage, because I will have to make 4 access to the memory in order to get the result. Okay? We went a bit down in the design, you know, I know you don't like that, you like stories which are high level, but this is also very important. Actually, did you ever learn about how you design a memory? That kind of things with multiplexers, buses, coders. Where? Which course?
Digital systems, computer organization.
Okay. But I'm not sure if you, okay, I don't know exactly what is currently the teaching material. But anyway, it's a good refresh. If you know it already, no problem. If you never heard about them, I think it can be useful. Okay? Whew. Then you see here a calculation which will tell you about the time that you need in order to access 4 locations on different memory models. Then if you have memory organization with 1 word and you want to get 4 words because your cache has 4 words, you have to do 4 times a full access. And you see, in order for the full access to happen is 4 cycles to send the address. Then we talk now about things which are slower. 56 cycles to get is the access time, and then 4 cycles to get the data back. Then I do 4 times that. If I'm widening the bus, I'm doing only twice. And if I'm widening the bus to have the cache line dimension, it's just 1 transaction. It makes a lot of difference. And if I do that story with banks, and I am looking for items which are consecutive, I'm sending the address, which is the one that I draw there, the 10 bits. Then I wait for 56 cycles. You know, Dutch is coming to my mind, because in Dutch you say the other way around. I don't understand why. 56, it's 56. It's 65, which is kind of, you know, I wonder how you can deal with that, guys, because I had a problem in the beginning with numbers, and I still have. When I hear a number in Dutch, I have to think twice. But in some languages, it's even worse. You know, in French, you say 80, it's 80, which is 4 times 20. And 90 is 80 this, which is 4 times 20 plus 10. Then, I don't know how it's in Chinese. It's 1, 2, and many. I don't know. I don't know how to count in Chinese. Then basically you have the startup, which is the same, and then you report 1 item at a time from each bank. And then this one is actually nicer. And if you put in the top of that you can play with the access, this structure is very attractive. Okay, now we finished that story, and we still have 1 part which will happen today and tomorrow, and I kiss you goodbye for this part. I'll certainly see you for the interesting discussion at the end of the journey, where you have to talk. You don't look very enthusiastic about that. And I wonder why. You'll actually have the opportunity to take revenge on me than to make me listen. I don't think you said a word today. Except, okay, I had something. Okay, now we discussed about single processors, and we'll look now a bit on multiprocessors and things which are related to multiprocessors. Now, somehow this is not a recent invention, even though you may think it is. Because you grew up in the time of Intel increasing frequency, and then you probably never heard about multi-core things before Intel brought them into your laptop. But that's from the previous century, in the, I think in the 6-7 decade. And it was together with the technology, a PCB-based technology. Then we put more processors in one rack, but on different PCB, you know, printed board circuits. They still exist, right? We have our processors on PCBs. And they were building them in the time the technology was okay, but somehow we gave up on them because they suffer from a problem, which is programmability. There is a small problem that we have as humans. We don't deal with concurrency in a proper way, in the conscient way. We do concurrent things in the inconscious way. You know, I'm talking, I'm looking at you, I'm moving my hands, which are parallel processes, but I'm not aware of them. If I want to write a program in a concurrent fashion, I have to think in a different way. And this is something that people have to learn from the kindergarten in order to change a bit the way of thinking. And because we are not trained in this way, we had difficulties in programming those multiprocessor machines, which we still do. But in that time, it was a matter of price. The price was high, the benefit, you know, the return was low. And then we gave up on it and we said, no, let's increase the frequency. Now we cannot increase the frequency any longer, and, you know, we return back. There is a saying that nothing is new under the sun. Somehow we have this tendency to return to things which we gave up in the past. Now today we have the same problem with programmability. They don't really deliver the incremental performance improvement, like if you have 2 processors, you run twice as fast, or if you have 10 times as fast. But we don't care, because there is no other way to run faster, and we don't really care for the price, and the overhead of communication is not as big as it used to be, because now they are on the same chip. Okay? Then practically we are revisiting issues that we had in the past. Some of them were not really studied because we didn't have the context to go that deep, but they were known. Okay. Now, what we want is we want to get calculation faster, and in order to get calculation faster on multiprocessor, we can do 2 things: to run more applications in parallel and have the impression that each application, you know, the final compound is running faster, or to split application in tasks and do task level parallelism. Now, some time ago, this is also from the previous century, but Mike is still alive. He was professor in Stanford. He's now retired. He's coming from time to Delft. He's a good friend of our group. And he came with a taxonomy of computers. And maybe you heard about Flynn's taxonomy, and his name is Mike Flynn, okay, because I said Mike, and it's not written there Mike, it's just Flynn. And he came with the idea that in this space, there are 4 possibilities. And he looked at the instructions and data flow. Then in a computer, what you have instruction flow and data flow. And depending on how you organize that, you can have the 4 possibilities. What we have, you know, standards is the uniprocessor. 1 instruction flow, 1 data flow. It's processed at a time. And now you can play with multiple data flow, with multiple instruction flow, and if you go for multiple data, you get vector processors. which used to be high performance specialized machine like, you know, Cray and other systems, but today you have vector extensions in your normal Pentium processor. You have multiple instructions, single data, which makes sense in the theory, but somehow not really in practice. And there are no implementation of such a machine, because somehow, except for some weird kind of application, you don't do multiple operations in parallel on the same data item. If you have an example of that, I'll be very happy to hear. No. And the last one, which is multiple instruction, multiple data, is the full-blown paradigm, and this is what we have today, plus or minus standard. Then you have parallelism at the level of the thread of the application, and you have parallelism of data. Now, okay, it's a bit difficult to see that, but this is a kind of diagram where you see the standard. You have controller, you have processing unit, and you have memory in all of them. And here you have one instruction flow, one data flow. On SIMD, which is the vector one, you have one instruction flow, which is now distributed to processing units, and then multiple data flow coming from the memory. Then processing units are of the same style. Then if I'm doing an addition, it's an addition on vectors, and then I'm getting, you know, n additions in parallel, then I'm adding vector A and B, and they are done on an item-wise level. My vector might be actually larger than n, and then I have to do some kind of tricks at the programming level. And I may also imagine that I'm doing kind of mixed operation in parallel, but that one will infringe the rule of single instruction. Then in here, I do multiple additions, multiple multiplications, multiple whatever in parallel. If I want to go for full variety, I go for the last one, when I may have more operations in parallel, and I can have even vector-wise operation. Then I can do one vector addition and one multiplication addition in parallel. Require more data items from the memory and more instruction things. Now, is that a general case? Is this covering all kind of processor organization that we can think of? How do you think?
So I have a question. The E5s and E7s from Intel, are they
Yes.
based on SIMD, the Bay version?
D
I
version.
think they are on D,
D version, okay.
because they have some data parallelism and they have also instruction parallelism. I'm not really interested in practical issues, you know. I'm a weird person. I don't know what kind of processor I have in my laptop. It's strange, right? But I think it's an MIMD core, because this is plus or minus the standard today. All Pentium, kind of old Pentium, they have the vector extension, then they have support for multiple data, and those are quad cores, then they have also multiple instruction.
And the 8 cores from the servers, are they
Are
also
the same.
same?
If they have vector extension, they are the same. If they don't have vector extension, they are only multiple instruction, but probably they have vector extension.
Thank
Then if you want to know precisely over products,
I have
you
to
are
search.
knocking on the wrong door.
Sorry.
Then, that was a kind of, you know, maneuver to disturb my attention. Then, do you think this is a general kind of structure? Actually, it's weird because this is a 4 quadrants diagram. In the same way, we had a 4 quadrant diagram for devices: resistor, capacitance, induction, and then the memristor was missing. And somebody, a Chinese guy from US, Chua, found the memristor, okay? And then the story is complete. Is this one a complete story? What do you think? It looks like, but you're not sure. Do you know what a data flow machine is? Then you have homework for tomorrow to tell me whether or not, what kind of machine it's a data flow machine. You just Google data flow processor. You don't look happy. You don't like homework. But it's not fair. You should work too. Not only me, but it will come the time. Okay. Now, in order to get advantage of this, what we call today standard approach, you have to have enough programs to execute, enough parallelism at a coarse grain level. Then if I have n processors and I want to utilize them, I should have n assignments to give them. And they can be like, applications or what we call processes or threads. Now, there is a difference between a thread and a process. A process is like an application running in its own virtual space. A thread is like a light process which does not have the own virtual space. It's running in the same virtual space with the other threads. Is that making a difference? From the concept of parallelism point of view, it does not. From the overhead of doing things around, it makes a difference. And it makes sense to do that. Now, if you don't have thread parallelism, your machine will die of starvation. Then you have somehow to find a solution to keep the machine busy. And you can do that by changing the application. Then you have to start rewriting it. Or you should have a smart compiler which should be able to understand the amount of processors which are available and to compile and link the application in such a way that enough threads are issued to the to the machine. Now, this may result in an under-optimal utilization of the machine. And just to give you an idea on this, it's not here. Okay, the slides are kind of a different logical flow than I had in mind, but I should have known that because I saw the slides yesterday. I also prepare my show. I have to know what's on the slides. Slightly, just an idea. Then what I wanted to let you see, it's probably later on, it's about the fact that if I don't have very, very full parallelism, I'm really underutilizing the machine. But before doing that, let's move to this. Now, if I have more workers, they do the job, but they have to have data to process, and they have to have a possibility to exchange things, because very seldom processes or threads do not talk to each other. Most of the time they talk to each other, and actually they talk too much. And this is bad for the performance. If you can split the application in threads, which are starting at moment 0, and they never join again before the end, then you have really nice parallelism. But most of the time, you have to do forks and joints and forks and things like that, and this will have an implication on the... Now, in order to have the data, to exchange data, you have to have a common memory. Then you have to have a place, it's like a blackboard, where you should put things for the others. And there are two flavors of that. And you can have shared memory, which is centralized, and all the processors have access to that memory in the same way. Then the access time of the processor to that shared memory, it does not depend on the position of the processor. Then that's the reason why we call that uniform memory access or UMA architecture. Then nobody is discriminated. All of them have access to the memory in the absence of contention. If there is contention, there is an arbitration going on, because, you know, if we talk in the same time on a bus, there is no music. We get a noise. Now, these symmetric microprocessors or UMA kind of architectures are assumed to be in general easier to program than distributed memories. And they look essentially in this way. You have processor, each processor has a bit of a local memory where, you know, I have a cache, and if I want to do good job, I should work there almost all the time. But whenever I have to talk with my friends, I have to get to the main memory. And in the main memory, I can leave messages for them, I can get data, or, okay? And then what you see is that there is a bottleneck in here. Then if we all want to talk with the main memory, we have a problem. Then as long as we can be separated, things are nice. When there is too much traffic on that bus, you may have more buses, but the story will be the same. Then this kind of structure is good as long as you don't have many processors, because this is not scalable. When you increase the number of processors, the performance will decrease because the bottleneck will be on that. And what you see, you also have an input-output system, which I didn't speak about, you know, in an explicit way, but this is where the disk is coming in the picture. Then the virtual memory is going on that. And you have that too, because the main memory has to be fed with pages from the virtual memory, which somebody has to take care of. And this is one model. Okay, now you also have what is called a distributed memory. And then this is larger, and this one can accommodate more processors, but in this one, the interconnect is different. And because it's, you know, in a bus, it's very simple. Regardless where I am, I make a bus request, the arbiter will give me eventually the control of the bus, and I'm doing a transaction, and from my place to the memory and back, it will take the same time. If you go in a distributed memory multiprocessor, I don't have a bus any longer. Then from where I am to the memory, I have to go via a certain route, which may be shorter or longer depending where I'm positioned. And I can use for this kind of interconnect a kind of mesh, a hypercube, factories, whatever. Today we even talk about 3D stacking. Then you take chips, you put on top of each other, you connect them with true silicon vias, and then you make a communication in a 3D network. And if I'm here and I want to communicate here, it will take certainly a lot longer than if I want to communicate with the neighbor. And this, it's a distributed memory multiprocessor. You see, I have a local memory. All of them have a local memory. And there is no real common memory because everything is common. I may have a player in this structure which is a memory module, which is not in this example. Then as opposed to the previous case where I had processor, cache, no other local memory, bus and main memory, in here every processor has a cache, which I don't see it, and a chunk of memory, which is available for all the guys. Then I cut the big memory in parts and I chop it and I give everybody a piece. I can also put another larger memory, which could be a second level of hierarchy if I want to, as a player in this case. Now,
But
yeah, but
how can you chop the I/O systems to? Because you said there's a
each
Yeah.
of them, it can get actually, then this is like, you know, it's a replication of the main memory in each node. Then each node has a cache, a main memory, which is a part of the huge main memory, and each main memory can now request things from the hard disk. Then on this one, you have a bus, and in that bus you have the players, which are processors, memory, and I/O. Okay, and here you have a DMA kind of controller and things like that. Now, in this case, this is replicated. Then each node has the possibility to do the local management, the virtual memory things, and now each local memory, it's available to the neighbors, but it's available via a network or via a switch or via some kind of communication structure, which is the blue stuff. And depending on how I do that, I might have, you know, I could have a fully connected structure. Then each processor gets direct line to connect, talk with all of them. That's very expensive. And what we do most of the time is we put here a network on chip with some routers, and I start from here and I go there and then I go here. And I apply all the tricks from communication, like, you know, wormhole routing, virtual cut-through. Never heard about? You did?
Networking,
Yeah,
yeah.
sure. Even if you did, you will. Okay? Now, which one do you like? This one or the previous one?
This one.
This one. Why?
Because it can work faster. This is
Are you sure it
okay.
can work faster?
I assume so.
I think can cause many problems, many conflicts. Like you don't know how many times you have to approach the other processor's memory, and it might take more time. You don't know. Depends on the program, doesn't it?
Yeah, that's true. But there are different kind of problems. Yes.
I think maybe easier to think about when writing programs.
On this one?
So you only have to, you can think about each one as a separate unit that sends messages to each other instead of thinking about the memory and thinking about what would happen if one starts to write before the other starts to read and
Then that kind of problems you have anyway. When you share things, you may have hazards. And you may have a lot of problems. And this is actually the big problem with those systems. There is contention at the memory level where you may actually damage the data. And there are two types of things. You may do operations in the wrong order, or you may use data which is actually not the latest version of it. And then, regardless of the model that you are using, you have to deal with those. And there are different protocols for that, which are increasing the overhead of communication and other things like that. But now if I look at those two, you know, both of you are right in one or another way. What I really see as the big advantage of this is that it's scalable. And then I can put more players in this. I can also deal with the way of the interconnection in such a way that I adapt the structure a bit to the application requirements. If I'm running a system in such a structure, and if I'm running an application in such a system, and only that application, I can decide plus or minus on how to make the interconnect in order to facilitate communication between nodes which are communicating more often, which I cannot do in a bus. And the problem with the bus is the fact that it's getting in saturation when I have too many players. As long as nobody wants the bus, it's fine. But in order to communicate with the others, you have to go on the bus. I'm speaking about the previous. Then, if I want to talk, I have to go to the bus. There is no other way. And there is another problem in here, you know. I'm looking for a data item which is in my cache. But that data item can be also in the cache of, let's say I'm the last processor, and it can be also on the cache of processor, the first processor. I need to know whether or not my item in the cache is the latest version of that. Maybe processor 1 has the latest version of that data. And if that's the case, I should be aware of. And for that reason, there is a kind of coherence protocol which is running, which will let me see that even though the cache line that I'm looking for, it's in my cache, the data item that I'm looking for, it's actually invalid, which means I have to reload it from the main memory because there I have the right copy, or somehow I have to ask processor 1 to give it to me. And in here there are a number of protocols which we'll talk tomorrow about in more details on how you do those. And you can do things like, you know, when you change a value, you check if other people do have a copy of it, then you make a broadcast in the bus. Then let's say processor 1 is doing processing and is changing a location in the cache. And then instead of writing back in the memory, which could have happened, you know, in a normal system, which write through, I can do an update at the level of the caches of all the others. Then I put the address of the location and I put the new value on the bus, and the other guys, if they recognize that address, they will do an upload in their cache. Then I'm doing a broadcasting with the new value of the system. Now, if I have such a bus structure, broadcasting it's easy. In such a common communication mean, it's easy to shout and to talk to everybody. Then broadcast on such a bus is simple. Now, doing that thing with the kind of synchronization between caches will solve my problem that I will always work on the right data item, but will create a broadcast here. Now, this may also saturate the bus. The same story may happen in here, because I also have locations, and you know, I'm working on a copy of something which is here, and I don't have locally the last version. The last version should be here. And if I do the same approach with a broadcast on a network, things are a bit more complicated, because a broadcast on the network is not as simple as a broadcast on the bus. Then you see, buses are not always bad. Okay, now we'll stop here, and tomorrow we'll finish the story with multiprocessors. In the afternoon, I will look on the